Okay, we've talked for a while now about how if a function is increasing, its tangent slopes at given points on that interval are positive, and how if it's decreasing, tangent slopes on that interval would be negative. So let's just formalize this idea. If the derivative on an open interval is positive, then the function is said to be increasing on the closed interval. You might wonder about this difference between open and closed. Remember that we can't do the derivative at the endpoints of a closed interval, but we will still consider those points to be on the interval where the function is increasing. So if the derivative is positive, the function is increasing. If the slope of tangent lines is negative, then the function is decreasing on the open interval. So we know when a function is increasing and decreasing. So when can it change between increasing and decreasing? Well, obviously if it's increasing when the derivative is positive and decreasing when it's negative, one place where it could change would be when the derivative is zero. Okay? And the derivative is zero at horizontal tangent lines. But I do have a couple of horizontal tangent lines here, for example right here, where the derivative or where the graph does not change between increasing and decreasing. So a function may change between increasing and decreasing when the derivative is zero, or when the derivative is undefined. I've got a point here where there's no derivative, we've got a cusp, as well as when the function has a point of discontinuity. So I have an asymptote here, but the function did change between increasing and decreasing there. It was decreasing, then it was increasing, and another point of discontinuity, it was increasing, and then it was decreasing. So a function could change between increasing and decreasing when it's discontinuous or when the derivative is zero or undefined. But that's not for sure. We'll have to check that out whether that happens or not. Finally, just in terms of one term we're going to use quite often, the point or the term critical point means the derivative is zero or undefined. Okay, let's use what we've just talked about to analyze this function. This is a function we know the shape of from previous years. It's a cubic. You can see the function. You can see where it's decreasing, then increasing, then decreasing. So we're going to come up with that analytically using our calculus knowledge. So we're going to begin with increasing and decreasing because that relates to the first derivative. The first derivative would be 12 minus 3x squared. And when the derivative is positive or negative, it's decreasing or increasing. So if I were to find out when it's zero, that would be a possible transition point between increasing and decreasing. So the derivative is zero. When x is plus or minus 2. These are called our critical points. Remember, our critical points are points where the derivative is zero. These are points where the function may change between increasing and decreasing. Now to figure out whether the function actually does, I'm going to analyze this through a number line. And we're going to use this format quite often. And what we're looking at are comparing the sign of the first derivative to the effect on the original function. Okay, we need to know where the first derivative is positive or negative. I know where the first derivative is zero. It's at these points. So where it's positive or negative would have to happen somewhere in between. So I could simply plug in a value in between these two x values. So for example, at x equals 0, if I plug 0 into my derivative, I would get f prime of 0 to be 12, which is a positive derivative in this section. And a positive first derivative tells me that the original function is increasing. And then I could test intervals in the other two sections. Instead of testing intervals, what I could do is, if I actually know the shape of the first derivative graph, which in this case is a parabola opening down, and these 2 and negative 2 would be the zeros of that derivative, I could just look at where the derivative is above the axis, the derivative is positive, and where the derivative is below the axis, the derivative is negative. So the derivative is negative here because the derivative graph is below the axis, and it's negative here. A negative derivative means my original function is decreasing. So to summarize, f is decreasing when f prime is negative, and this occurs between negative infinity and negative 2. Remember, we include negative 2 in our increasing and decreasing interval, union 2 to infinity. There's no endpoint to infinity, so those are open brackets. And we are increasing when the first derivative is positive, which is everywhere else, between negative 2 and 2.